Hello, good people. This is a continuation of section 3.5 on implicit differentiation, coming from Calculus Early Transcendentals by James Stewart. And I wanted to do a separate video on the derivatives of inverse trigonometric functions, which you see before you. And wanted to go over how we use implicit differentiation to derive these derivatives. And I also want to go over some examples on how to use the chain rule with these derivative rules. Good. So I wanted to take a look and go over how the derivation of all 6 trigonometric functions can be done in the very same way. So I thought I'd start with how do we find the derivative of inverse tangent of x? And so we're looking for find dy dx for y equal to the inverse tangent of x. And we know that we can transcend that to be an implicit function by using its equivalent expression. And that equivalent expression means find y inside minus pi over 2 to pi over 2, where the tangent of y is equal to x. Remember, the tangent function inputs an angle and outputs the trig ratio opposite over adjacent. And so your inverse function is going to input your trig ratio and output an angle. But in order for your inverse tangent to actually be a function, you have to restrict the original function tangent of x so that it is 1-to-1. And that is naturally done using the very first cycle between the two vertical asymptotes of minus pi over 2 and pi over 2. And then we get all values of tangent so that we can consider putting all values of the trig ratio in the input for inverse tangent. All right, so now we've got this y equal to inverse tangent of x is equivalent to tangent of y equal to x, and this is an implicit function, right? So if this is an implicit equation, we need to use implicit differentiation to find the dy dx, right? So to find dy dx. And so here we go, and remember with implicit differentiation, y is implicitly a function of x, so whenever we have a term that contains y, we must use the chain rule if we're taking a derivative with respect to x. But all other terms in the equation that just contain x can get normal differentiation. And so here we go. The first step in using implicit differentiation is to take the derivative of all terms within the equation. And so here we go. The derivative of tangent is secant squared, and the derivative of tangent y is going to employ the chain rule, and we will have secant squared of y, but then times the derivative of the inside, and the derivative of y is dy dx. Then we say equals, the derivative of x is just equal to 1, and then our next step is to solve for dy dx. And so here I go solving for dy dx by dividing on both sides by secant squared. And we recall from fundamental trig identities, secant of y does equal 1 over cosine of y, so we know that cosine y is going to be 1 over secant y, and we have 2 of them, so we know that dy dx here is going to be cosine squared of y. Now, we started with an explicit function up here. Y was explicitly defined in terms of x, so that when we go to find dy dx, we're going to want an explicit expression in x and x only. So we could keep it this way with cosine squared of y, but we actually want to make it in terms of x. So we take back the implicit equation, and we're going to use standard definitions of tangent. So we'll take tangent of y equal to x. That's the same as x divided by 1, and we know that the definition of tangent y is opposite over adjacent in a triangle, right? So if we have our little right triangle here, we know that if y is the angle, the opposite side is going to equal x, and the adjacent side is going to equal 1. And then by Pythagorean theorem, we can see that the square root of 1 plus x squared is the hypotenuse. Now our derivative is dy dx equal to cosine squared of y, and I see that from this triangle, cosine of y is by definition the adjacent over the hypotenuse, and the adjacent over the hypotenuse is 1 over the square root of 1 plus x squared. So if I return to my dy dx, which is equal to cosine squared of y, that's the same as cosine y squared, and that's going to be the same as 1 over the square root of 1 plus x squared squared, and we now can simplify that and see that it is 1 over 1 plus x squared. Good. So all of the other inverse trig functions can be derived using the exact same process. You would want to take your explicit function and transcend it to its equivalent expression. It turns it into an implicit equation. We then use implicit differentiation to find dy dx, and then we take our original substitution or our original tangent y, and for example, if you were doing inverse sine, you would have sine y equal to x, and you would put them into a triangle, and you would take your dy dx expression and make your appropriate trigonometric definition substitutions. And that's how you can get it back to its explicit form. So I want to go over some examples of the chain rule and how we employ the derivatives, or employ the inverse function derivatives using the chain rule. So here's some examples here, and we can do number A or letter A. It says find the derivative with respect to x of inverse sine of cosine of x. So we're going to be using this derivative, and so remember our outside function is going to be inverse sine of. And so if I'm going to take the, if I have y equal to inverse sine of cosine of x, again, my outside function is inverse sine of x, so my y prime, I'm going to take the skeleton of my entire derivative here, and I'm going to get 1 over the square root of 1 minus squared. And notice that whatever this x is what this x is. And so that's why I leave a space for that. So remember our chain rule, it's the derivative of the outside, evaluated at the inside, but then times the derivative of the inside, right? That's my chain rule. And now it's just a matter of simplifying that expression, and I know that 1 minus cosine squared does give me sine squared. So this is going to equal minus sine x over the square root of 1 minus cosine squared is sine squared, and then the derivative, or the square root of sine squared, is just going to be sine. And what do you know? This answer ends up being negative 1. Okay. Now I can do B here, and it says find R prime if R of t is inverse secant of t, and then times square root of t squared minus 1. Good. So this employs the product rule, and remember, if that's my product rule, then I'm going to have y equal to the derivative of the first times the second plus the first times the derivative of the second. And if I just make a little table here, if I've got f equal to inverse secant of t, then f prime, and I go up here in my inverse secant, is going to be 1 over x times the square root of x squared minus 1. So this is going to be t over the square root of t squared minus 1. And if we have our g here equal to t squared minus 1 to the 1/2, don't forget our chain rule here. Our derivative g prime is going to be 1/2 times t squared minus 1 to the minus 1/2. That's the derivative of the outside, but then times the derivative of the inside. And if we cancel our 2's, we end up that g prime here ends up being t over the square root of t squared minus 1. So when I go and take my product rule, my y prime is going to be the derivative of the first times the second plus the first times the derivative of the second, right? And so I'm just going to plug in my values. So sometimes it's good to make a table separately in order to put them in. So what's my derivative of the first? That's going to be 1 over t times t squared minus 1. G is going to be the square root of t squared minus 1. Our first is going to be the inverse secant of t, and our g prime is going to be t over the square root of t squared minus 1. We then want to clean things up, and in cleaning things up, I just see that my square root of t squared minus 1 cancels from the very first term, and so my final answer would be y prime is 1 over t plus the inverse secant of t, and I do want to put my t in the front there. Just make that a little neater. Over the square root of t squared minus 1. And that is my answer. Merry Christmas, people, the green and the red. All right, the last one looks like I've got chain, chain, chain. So we might want to take this to another page, and I'm going to take it to another page so we have nice room down below. All right, here we go. Find dy dx if y is equal to. So I notice that I have an outside function, and my outside function here is x squared. And I also have another function, so this is going to be a double chain rule. And it might be helpful to find that derivative first. Good. So let's say, for instance, my g here of x is going to equal the inverse tangent of 2x plus 1. So what's my derivative of g prime? Because I'm going to need to do that derivative. My g prime, because the derivative of the inside, right, using my chain rule. I know that the derivative of inverse tangent is 1 over 1 plus x squared. And so keeping in mind, just coming back to that derivative rule, whatever this x is what this x is. And so we want to make that substitution, right? So I'm going to make that outside, the derivative of my outside, and it's going to be evaluated at the inside. Oh, and I still have a squared on the outside there. But then times the derivative of the inside, and the derivative of the inside is 2. Good. So I'm going to keep it like that just for a second, and I'm going to say that this is 2 over 1 plus 2x plus 1 squared. And that's my g prime of x. All right, so notice that this function here is y equal to, right, inverse tangent of x, but this is going to be if it is an f of a g of x, then our y prime is going to be the derivative of the outside, evaluated at the inside, but then times the derivative of the inside. So the derivative of my outside is x squared, so I'm going to have 2, right, and that's in red, to the first power, evaluated at the inside, and the inside function is inverse tangent of 2x plus 1, because that's what g of x is, and then times the derivative of the inside, g prime. And our g prime is 2 over 1 plus 2x plus 1 squared. So you might want to just keep it in that way, just cleaning up by multiplying by 2 and 2 to give me 4 times the inverse tangent of 2x plus 1 all over 1 plus 2x plus 1 squared. And that's how you would play with chain rule with inverse trig functions. All right, hopefully that was helpful.